Okay.
Yeah, fine. Currently, we can see your PPT deck, and as usual, you may spend 1 minute to introduce yourself, and then you can carry on to present this paper.
Okay, thank you. Okay, hello everyone. This is Qi. I'm a second-year PhD student in computer science, and today I'm going to present the paper Daydream, accurately estimating the efficiency of optimization for DNN training. We have watched the author's Hongyu Zhu's presentation. It's a really good. Oh, sorry. It's a really good presentation. He presented clearly about the challenges of estimating the optimization for DNN training and how he solved these challenges. He also did a lot of experiments that can show his system can get good performance. So today I will just talk about like my understanding about this paper. First, I want to talk about deep learning a little bit to better understand this paper. Well, as we all know, deep learning is more and more popular these days. It has been applied to automated driving, medical research, industrial automation, and so on. So why deep learning is popular right now? Because it's simple and it works. The figure shows the differences between traditional machine learning approaches and deep learning approaches. For machine learning, you would have to design a feature extraction algorithm, which needs a lot of like heavy mathematics and is not very efficient, does not perform too well. The accuracy is not high enough for real application. Well, besides, after doing all of this, you would also have to design a whole classification model to classify your input given the extracted features. And for deep learning, it can perform feature extraction and classification in one shot, which means we only have to design one model. And to implement deep learning, we can use open source libraries like Keras, TensorFlow, and PyTorch. They are really convenient. So deep learning is easy to implement, can achieve high accuracy. So more and more researchers focus on deep learning right now. Researchers have come up with different architectures that can be applied in different scenarios. As we can see from this figure, this is from a paper in CVPR 2017 conference. They analyze and compare multiple popular like neural network architectures. For example, the VGG19 network has been applied a lot in image classification, and the ResNet 50 is designed to avoid overfitting problem. At the same time, can get high accuracy. While these two architectures are benchmarked by the author in this paper, well, as we can see, researchers have developed many important models at a rapid pace. We observe that the models tend to be deeper and larger in order to achieve high accuracy. This creates a huge demand for computing power. I will explain now. Well, to make sure the deep learning models performances, there are two major requirements. The first one is deep learning requires a large amount of labeled data. For example, automated driving requires millions of images and thousands of hours of video. The second one is deep learning requires substantial computing power. Training a deep learning model can take a long time, from days to weeks. Using GPU acceleration can speed up the process significantly. And high performance GPU have a parallel architecture that is efficient for deep learning. And when combined with clusters or cloud computing, this enables deployment teams to reduce the training time from weeks to hours or less. And this paper is more related to the second requirement. We also know when our data set is larger, the computational training cost will significantly increase. So now the question is how to do optimization to reduce the training time. This is this paper like focus on. System researchers have proposed many optimization. For example, improving the memory utilization, better overlapping of communication with computation, and also increasing the communication efficiency. Here, I will illustrate an example. So this figure shows the naive deep learning training process. Typically, the pre-process of the data occurs on the CPU, and the model will be trained on the GPU. The CPU will perform extraction, which extract the data from different data sources, like local data sources, which can be like a hard disk, or extract data from remote data sources, like cloud storage. And transformation, you will shuffle the data, create batches, apply vectorization or image augmentation. And the third part is the loading the data, involved like cleaning data, shaping the data into a format that we can pass to the deep learning model for training. As we can see from this figure, in the model training process, CPU pre-process the data to get it ready for the model to train, and GPU at the same time GPU is idle, and when GPU starts training the model, the CPU is idle. So it's not an efficient way to manage the sources. So we can optimize the data extraction, data transformation, and the data loading. Data extraction is optimized by processing multiple files concurrently. As we can see from the figure, so the train, read, and open, they are like at the same time. And the second way is parallelize the data transformation. For example, image augmentation is part of pre-processing. It happens on a CPU. So every augmentation, normalizing, and rescaling of the image it takes a long time. So it slows down the training process. So we can run all these image operation by utilizing order curves by processing them parallelly. We can also prefetch the data by overlapping the data processing and training. As we can see, there are many optimization methods available. However, these proposed optimizations cannot be fully implemented due to two reasons. The first reason is when applied to different deep learning models and deployment configurations, the efficacy of optimization change a lot. Also, differences in deep learning models also like accelerate type can also shift the major runtime bottlenecks. Second is also onerous and error prone for programmers to implement and evaluate various like optimization. And it's difficult to find like which one is actually work for their models. So it's common for users to ask what if question. I only list one. Is will optimization X improve the performance of my model? The basic approach to explore this question is is like at first we need to decompose the workloads into atomic tasks and then profile the runtime statistics for each task and then model what if question. We use the simulation to estimate the performance. To implement this approach, there are 3 key requirements. The first one is we need to track dependencies at a kernel level abstraction. For example, one GPU kernel corresponds to one task. In this way, we can improve the hardware utilization. Meanwhile, we have to consider the both CPU and GPU runtime. Second, we need to map tasks to DNN layers. Here, the paper used the tool CPU TI to get the details of the CPU and GPU tasks. And third, we need the ability to easily model diverse DNN optimization, like scaling or shrinking tasks, duration, and also some like other complicated transformation to the dependency graph. So this paper proposes Daydream to estimate the efficacy of optimization for DNN training. The system has 4 phases: trace collection, dependency graph construction, graph transformation, and runtime simulation. The first one is trace collection. So Daydream used the tool CPU TI to collect low-level profiling details. It can provide details for all the CPU and GPU tasks, include the name, starting time, duration, and also the CUDA stream ID and the thread ID. And there are 5 types of dependencies for accurate simulation. The author has presented a lot in the video. I will just like pass. And the paper designs a set of primitives, insert, remove task, select, and schedule. With these primitives, is already like sufficient and flexible and accurate for us to estimate the training time. And then we can do the runtime simulation. The simulation determines the start time of each task and record the total execution time. Okay, thank you. That's all my presentation. Thank you for the listening.
Okay, thank you, Qi, for your presentation. So in the author's presentation, he mentioned that the first step he need to do, they need to track the dependencies. So from your understanding, why this step is mandatory, or what's the usage for this step to track the dependencies?
Thank you for the question. Well, the author like the first they need to track the dependencies. It's like the GPU in this thread, the GPU and it divide this task into